And we're live. Hello, people. Actually, is there anybody there? Hang on. I just got to get a little bit oriented here. Welcome to the live stream. Oh, it says right here, nobody's watching. Awesome. Let me just interact with all the people in chat. Yeah. Okay. Well, let's get this underway. We could look at me or we could look at the math more. So I'm kind of fun to look at, but let's see what this looks like. That's a little bit better. Let's do it. All right. So, yeah, but you go to YouTube. You want to see a face. It's too much of me. How do I fix this? Okay. There you go. I don't know. Whatever. Nobody's here to complain. So let's just hope that my thing works here. All right. So hang on here. We're good. All right. So what's the plan here today? The plan here is to talk about the Fibonacci sequence. And you have to say Fibonacci like that, okay? If you're going to really do this properly. And, I got to admit, there's a whole lot here. And I don't know if I can live up to the thumbnail all within a short period of time here. I mean, it's going to be long if I do. Especially since I'm not even going to get right into it. I'm just going to meander about the Fibonacci sequence. We start with a 0 and a 1, and you've probably seen this before, hey? And then we add the 0 and the 1, and we get 1. And then we add the 2 1s, and we get 2. And hang on here, shut that off. And we add the 2 1s, we get 2. We add the 1 and the 2, and we get 3. And you get the picture. 2 and 3 get 5, and so on and so forth. And the thing is, not everybody starts with the 0. And actually, I wasn't going to start with the 0, but then I ended up doing that. But you've got these purists that say, oh, you need to start with the 0, or you need not to. But the thing is, there's nothing magical about this as a starting point, because we could go backwards. Like 0 plus what is 1? Well, we could put a 1 here. And then what plus 1 is 0? -1. And then we could put a 2 here. So we could, so this isn't like a magical starting point, but it is fun now to see how far you can go back this way, because you got to think backwards. So actually, you know what? I'm even gonna scrap the 0, and we're gonna talk about the Fibonacci sequence going forward like this. And at the risk of really delving right into it, because what are we doing? We're looking for the nth term, right? And if this was a arithmetic sequence, we would be just adding the same number each time, plus 5, plus 5, plus 5. So if you want the nth term, you go, okay, 5 times n. And you go, let's just add all that. But it's not an arithmetic sequence. Something else that it's not, we'll just spend some time talking about what it's not. Something else that it's not is it's not a geometric sequence, in which case you multiply. So if you want the nth term, you just multiply by n. You multiply by the common ratio. So like maybe it's you're tripling each time, that you just multiply by 3 so many times. But we don't do this either. But the cool thing is, what I want to notice about this is it does tend toward a but it doesn't start out with it. It moves towards it, and I want to show you that. What's this thing? Mother's Day 2001. Yeah. Okay. So let's let me show you what I'm talking about. Okay. So let's start here. So what's our general rule? So our nth term, let's just call it a_n. Okay, that equals the sum of the previous 2 terms. So n minus 1 plus n minus 2. Okay, so there's the 5th term. It's the sum of, this term here. It's the sum of these previous 2 terms. Okay, all right. And so we do have an algorithm for figuring out the nth term. We could just keep on adding these until we get to n. Okay, the idea is, let's see if we can figure out something a little bit better. If we can compact all that work into one formula, then that just churns it out for us for fun. But what I want to show you is that it does approach a common ratio. All right, so let's say we've got so let's say we've got two terms. Okay, we've got I mean, what's the ratio here? 8/5. Okay, so but 8/5. Okay, that's not the same as 5/3. 5/3, and that should be just a not equal sign. Okay, but as you go on further, it's going to end up being something, and let's discover what that something is. Because yes, when you have a long discussion ahead of you, you start out by talking about things that aren't it. So we're going to take the ratio between a term and the term before it. So a over n and a over n minus 1. Okay, and it approaches this equality, but it's never actually going to be there. Hey, so let's take a n plus 1, and that's that. Okay, so these two ratios will get closer and closer to being together as n approaches infinity. So my thing is, let's assume that they are equal and see what we end up with. So we get this thing. We'll cross multiply. Hey, so these that multiplied by that should be equal to that multiplied by that. So let's just do that. So a n squared equals a n plus 1 times a n minus 1, and that's all she wrote. All right, so let's now move this over here, and let's move this up. Yeah, I'm going to regret doing this because we don't need all any of this to figure out the nth term, but this is my live stream, and I get to do whatever I like. And so I'm going to do that. But it's not going to match the thumbnail, and people are going to then click away, and they're going to be all mad. But I say, too bad. Okay, maybe I'll change the thumbnail. Okay, so this squared minus that times that equals 0. Okay, now I'll have a swig of the Batman coffee. No, where does that get us? Well, not very far. But you know what? Let's do our best to redefine everything in terms of this a n. Because remember, what does a sub n equal? It equals a n plus 1. Was it plus a n minus 1? So yeah, you subtract these and you're going to get 0. But let's do something a little bit funkier. Let's take this a n plus 1, and let's do this. A n minus 1 times, I don't think it's going to work, equals, okay, equals a n plus 1. Sorry, that should be minus a n minus 1. Okay, a sub n minus a sub n plus 1. Okay, so now I'm going to take that and I'm going to put that into here. Okay, so then we get a sub n all squared minus a sub n plus 1 times a sub n minus a sub n plus 1. And that all equals 0. Okay. You might be going, why would we do a thing like that? Aha, because next, and let's move forward, and let's get rid of this swill from the bottom. And if nobody else shows up, I think I'm just going to finish with this, and we'll change the thumbnail, or we won't continue with it. So if you're here, say hi. Nobody watching. Okay, so we'll do it anyway. This video is going to really wreck my stats. Okay. So let's do this, and let's do that, and let's do that. And now we're going to multiply all this out for reasons that you are wondering about. So now we got a sub n. Okay, I should have that squared like that. Minus, and let's multiply this out, a n plus 1 times a sub n. Distribute that. So that's going to end up being plus a n plus 1 all squared. And that equals 0. Okay, so this, with all of these a's and all of these n's, it's really kind of a mess. So here's what I'm going to do. Okay, I am going to say that a sub n is some variable x, and I'm going to say that this one that follows it is some constant, which we're going to call k. I'm going to rewrite this. So now we've got x squared minus kx plus k squared. Okay, and I'm even going to go further and say that k squared is no, I'm trying to simplify it. I may end up complicating it. Okay, the point is that now this is a quadratic where a equals 1, b equals minus 1, and c equals k squared. Oh, somebody watching! Yay, person watching! Yay! Please say something. Get me on track. Okay, now I'm going to have to do something quality. Hello, person watching. Thank you so much for showing up. If you say something, I'll interact with you. Maybe that's going to embarrass you, make you go away. Okay, I know you were probably hoping to see the nth term of the Fibonacci sequence, but right now I'm just playing with it, and I'm showing what common ratio it all tends toward, even though it isn't a geometric sequence. Okay, so we got a equals 1, b equals -1, c equals this. So you know what? Let's solve. Oh, remember, all that equals 0. So let's just solve that. So x equals negative b. Yes, it's the quadratic formula. You thought you'd seen enough of that. Plus or minus the square root of b squared minus 4ac, and that's all over 2a. And let's see, so at negative b, so negative 1, so that's 1, plus or minus the square root of b squared, so that's -1 squared, so that's going to be 1 again, minus 4 times a times c. Let's spell all that out. 4 times a, okay, times k squared. Okay. Okay, and that is that. Oh, so that's going to be all over 2 times 1 is 2. So let's move this forward, and and so that equals 1 plus or minus square root of 1 minus, we'll just do 4k squared all over 2. So this is what your common ratio is tending towards. But what is this k squared? You know what? This worked out a lot better than last time I did it. What is k squared? K squared is the square of the one following n plus 1. Okay, you know, when I did this before, I'm so sorry. I used different numbers, and this actually ended up being 5. This whole thing in here ended up being 5 because it's supposed to end up being the golden ratio, and I screwed up. So there, welcome to live streaming. And now there's 2 people watching me screw up. Hi, Wolf. I'll scroll back so you can see what I tried to do. And I totally messed up here. But the point is, it's not part of the thumbnail anyway. So yes, hi. Thank you for showing up for my pathetic live stream. I'm sorry, I shouldn't be so self-deprecating. I don't know if you've seen this before, but what I'm trying to show is that with the Fibonacci sequence, the ratio tends toward it's not a geometric sequence, but as the numbers get larger, it tends toward the golden ratio. But what I must have done wrong here is in choosing how to represent this ratio here. This a over n. Which 2 to put here? A over n divided by a over n minus 1, and a to the n plus 1 over a to the n. So this is your generic ratio, and as n gets larger, these get closer and closer to being the same. And then I cross multiplied and did a little bit of substitution and created a quadratic. But my problem here is with this k, because when I've done this before, the k doesn't end up being a mystery. So it's a matter of choosing how you represent this and what substitutions to get. And I thought I would remember how to do it, and then I forgot that you have to be careful about what you choose, because this business in the middle, it's actually supposed to work out to something, but it didn't. But the good news is we don't need that for what we're going to show. So, and you know what? This is a live stream. So if you say something, hey, Adam, let's do something else and let's take it in a different direction, that's all cool, because I set this thing because I don't know if anybody's going to show up and interact. So I'll just keep on going. And show you what the plan is to find a general term for the Fibonacci sequence, and or at least get as far as possible into that, because there's a fair bit involved. So what I'm going to do here is I'm going to rewrite the Fibonacci sequence 1, 1, 2, and you're wondering why am I writing them so far away? 3. So 2 plus 3 is 5. 5 plus 3 is 8. And there you go. And what I'm going to do, okay, is I'm going to encode this. I'll call that S. And I can get rid of that. Oh, no, hang on here. Maybe I can't. Yeah, whatever. Okay, what I'm going to do is I'm going to encode this into a power series. Okay, so I'm going to sneak each of these terms into a power series. So that's going to be x naught. That's going to be x1, x to the 1. That's going to be x squared. That's going to be x cubed. That's going to be x to the 4th. That's going to be x to the 5th. And I think you get the picture, eh? And it keeps on going on forever. And we're summing this. Okay. And we're going to ask ourselves the question, can we find a closed form representation of this power series? Okay, and by closed form, I mean a bit of a cheat that we can all write down in one spot rather than have it go on forever. And the closed form is not going to be the exact same, but it's going to tend toward the sum of the power series in a particular place. It's going to work in a particular place. You know, none of that makes any sense until I show you what I'm doing. So now I'm going to, this is wonderful, but now I'm going to multiply this same series by x. Okay, so now I'm going to get 1 times x to the power of 1. So I'm going to put that, I'm going to put that over here. Okay, x to the power of 1. So the x to the 0 is gone. And then this one here is going to become 1 times x squared. Okay, and this one here, it's going to become 2 times x cubed. 2 times x cubed. So you see, I'm just shifting everything over to the right when I do this. And this might seem familiar to you if you've done like the generic power series, when you're proving something like 0.99999 equals 1. If you've done that before, this might seem familiar. So what am I going to have here? I'm going to have 3x to the 4th plus 5x to the 5th. And I've just shifted everything over. So these numbers match on the diagonal. They're out of, the numbers are out of sync, but the powers are in sync, because eventually we're going to do some subtracting here. And now I'm going to take x squared and I'm going to multiply that by s, which is the sum. Okay. Nice to know I've still got 2 people. Yay. Okay, so what's going to happen here? What's going to be all these same numbers here? So I'm going to write out the numbers first. 1, 1, 1 plus 2 is 3. Oh, hang on here. I messed up here. No, that's 1. What's what? That should be a 2. That should be a 2. All right. So 1 plus 1 is 2. 1 plus 2 is 3, and on forever outside beyond the board here. Hey, okay, plus, and I need to put in the numbers here. So that's going to be x squared. That's going to be x cubed, and that's going to be x to the 4th. That's going to be x to the 5th, and we sum everything. I should put the plus signs in here too. Plus signs, plus signs, plus signs. Alrighty. Any questions? Yeah, it's cool. I'm going to assume that you follow all this, that I'm being somewhat entertaining. Let me just drink out of my Batman mug. Say hi again if you're still watching. Okay, so what am I going to do here? I'm going to now take the s, and I'm going to subtract this, and I'm going to subtract x squared times s. Okay, and so what do we end up with? Okay, so really what we're doing here is we're subtracting that, and we're subtracting that. Okay, and now we might go, why does it do what it's about to do here? But let's look at this. So we end up with 1 over, we end up with 1. Okay, and then 1 minus 1, this minus this, that it ends up being 0. 2 minus 1 minus 1, that ends up being 0, and so forth and so forth and so forth. And why did it do that? Because of course these two add up. The bottom ones are the 2 prior coefficients. So that's how we defined the Fibonacci sequence. Now I'm going to end up with a 1 here. No, sorry, that's going to end up being, yeah, because that's 1 times x naught. But you know what? I'm going to do something that's going to make everybody upset. I'm going to actually start my power series with that being 1. So that's going to increase, because I don't know what this is how I've done it before, and I don't want to be creative here. So it's the same thing, except I'm doing the power series over here. Okay, I'm just moving everything over. So I'm redefining s, right? Because that's always fun when somebody's showing you mathematics and then they redefine everything. Okay. The other thing the way I was doing it might work. It might work even better, but I don't want to risk it right now. Okay, so instead of this being 1, it ends up being x. Okay, so it boils down to x. And as I said, this might not make it any easier, but it makes it more familiar for me. So let's do it that way. So let's move this over here, and let's just kind of summarize what we got. So we've got the sum of our power series, which in this case starts not with a constant, but starts with 1 times x. Okay. And we subtracted from that, we subtracted x times the sum and then x squared times the sum. So we end up with this thing. Okay. And then now let's factor out the s. So we end up with s 1 minus x squared, okay, equals x. Okay. And then now we do the trick. The trick is, let's just divide everything by this polynomial, by this quadratic. So all this is here is going to go underneath here. So we end up with s equals x over 1 minus x squared. Okay, and then you'll see that that's a closed form expression of our infinite power series. But now realize it doesn't have the same domain, because somewhere this polynomial down at the bottom is going to be worth 0. Okay, depending on what the x is. And in a moment we'll factor that and we'll work out what that is. So it doesn't have the same domain. Okay. So what this closed form does is it's going to tend towards, and actually I'm going to bring up Desmos and I'm going to add that to our stream here, so you can see what I'm talking about. You know, instead of just watching me do this, I mean, go to Desmos and bring this stuff up yourself, or whatever. I don't know if you guys are used to using Desmos, but I totally recommend it. I don't know where people are at or whatever. Yeah, you're still here. Thanks, Wolf. Yeah. Okay, question for you, Wolf, if you don't mind answering. Where are you in your mathematics journey? Are you like first year college, or are you before that or after that, or just an old guy with a beard who likes to do math, which means we have something in common? Then it helps me know who I'm talking to. You don't have to say anything though, no pressure. Okay, but I'm going to bring up Desmos here right away. So I got to go into StreamYard, and going to bring up a new. That's too much of me. I'm going to share screen. Oh, you're an electronics engineering student. Okay, so that's very cool. So you're doing some calculus, I imagine, or you're going to be using I. You're going to be using complex numbers. I betcha. Okay, Chrome tab. Okay, are you familiar with Desmos? So I'm just gonna. Here's my. So what did I do here? So I've got 1x plus 1x squared plus 1. I'm just going to write as much of this as well. I'm going to write some of this so we get an idea what it looks like. Third plus 3x to the fourth plus 5x to the fifth plus 6x. Sorry, no. See, I get mixed up. I start adding the wrong things. 8x to the sixth, and I'm going to do one more. Actually, now notice, take a look here. The left-hand side of this, what it does every time, the left-hand side of this graph, what it does every time I add something. I add a term. Plus 13x to the seventh. So this part on the right, it stays pretty much the same, but what's happening to the part on the left? And think about why it's doing that. 21x to the eighth. Okay, so the left is bouncing up and down. So we don't entirely need to know why it's doing that, but you got to ask yourself the question: why is it doing that? Why does it do that? And it's a reminder that this power series, it's closing in on something. Okay, and so let's give this a name. Let's call this partial sum here. We'll call this f of x. Okay, And now let's take a look at our, we'll just call it g of x. Okay, equals x over what was it? 1 minus. I just got to go take a peek at it. 1 minus x squared. 1 minus x squared. Oops, that's supposed to be squared. Okay. So the blue. This one here, here's our closed form, okay? And I hope you're seeing that. Yeah. Okay, here's our closed form. And I mean, it's very different, but between here and about here, it approaches the infinite sum. And that is what we're after. It's so, I mean, to me, I think it's so neat that right here, like right here, it just jumps away from it. I mean, when it's outside what you call the radius of convergence, it doesn't kid around. So it's not even going to bother to try over here on the left side. But on the right-hand side, it's going to get closer and closer and closer and closer and closer to the blue. These two lines are going to get closer to each other. All right. So this is good enough for us. Okay, this g of x that we've converted it to. And the idea is the power series that we started with, in which we encoded the Fibonacci sequence, okay, that original one here, okay, I mean, we can't just pull the nth term out of a hat, okay, without having to go through this whole process. And so now we've got a closed form, okay, but we're going to take that closed form and we're going to, this is why I was saying this is really long. We're going to convert that into another power series in which the terms are easier to predict. Okay, in order to do that, we need to factor this baby down here. And, you know, I'm going to pull out, a negative x, because I would rather have this leading coefficient. So times 1 to 1 over, I'd rather have this be positive, eh? So now we've got x squared plus x minus 1. Okay, so let's factor this. Let's not do anything fancy with this. Let's just use the boring old quadratic. So what is it? We got a equals 1, b equals 1, c equals negative 1, and then let's just go with this. So we've got x equals negative b plus or minus square root of b squared minus 4ac all over 2a, and there's probably a song that goes with that too. Okay, and that equals, okay, so what's negative b? Negative b is negative 1. Okay, b squared, hang on here. B, yeah, because b here is, let's make sure I'm not messing up here. So a is positive 1, b is positive 1, and c is negative 1. Okay, so negative 1 plus or minus the square root of 1 squared. See, this might seem familiar from when I was trying to show the ratio that it was going towards, the over celebrated phi value. B squared minus 4ac, so 4 times 1 times negative 1 all over 2 times, oh sorry, 2a is 2 times 1. So that's going to get us, okay, negative 1 plus or minus square root of 1, blah, 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 blah. So this is going to end up being 5 in here. 5 all over 2. Okay, so let's go back into, oh man, you can't even see this because I'm looking at the wrong thing. Yeah, I know, you still see Desmos. Oh my goodness. Oh crap. Okay. Okay. Yeah, I'm still getting used to StreamYard. I will go back and show you what I did. Man, because I was just going to go back to Desmos and then demonstrate that. I'm talking away. Yeah. Alrighty. So, yeah. Okay. Nope, that's just too much of me. Share screen, and we're going back to the Chrome tab. Thank you for the feedback. Okay. So what did I do here? I was going back here. I said, here's our sum. Okay. And I divided everything by this quadratic. And so now I have an closed form expression for the sum. And I rewrote it with this negative x over here because I thought this would be easier to factor. And so now, so I factored it away, okay? And I end up with this thing here. So now I'm going to go back to Desmos, and I don't know if you recognize this, but I'm going to go back to Desmos, and I will let you see what I'm doing too. Oh my goodness. Okay, invite. Says 2 people are watching. I'm wondering if I'm one of them. Share, stop screen, stop share, and then now we need to go back to Desmos here. Okay, so let's take a look at that. So let's do negative. We'll put that in parentheses. -1. We'll do plus square root of 5. Okay, and that's all over 2. Okay, does this look familiar? And then we have -1 minus square root of 5 all over 2. Okay, so what do we have here? We've got the golden ratio, but it's the negative of it. Okay, if you're familiar with the golden ratio, I don't know, but what we're going to do here is we're not going to keep writing this thing out the whole time. So we're going to use the standard terminology for this. So you know what? Let me do something here. I'm going to put this negative here, and then we'll make this minus, and then we'll put a negative here, and then we'll make all of this plus. Okay, and let's put the negative in front here. Okay, I sure hope you're seeing what I'm doing. Yep. Okay, there we go. All right. So this is your famous golden ratio. So let's call this P equals that for phi, because I don't feel like writing out phi. I probably could, couldn't I? Hang on here. What if I write out phi? Oh, I likes it. Okay, and then we'll call this one phi. I want to call it phi bar, but I'm just going to call it phi sub 1 here. And that equals this. Okay, so now we've got the golden ratio. Oh, no, we don't now. What happened? That was the minus. Our minuses got messed up. Let's just put that there and that there. Why is it being mean to me? So this, we're going to make this let's make that phi 2, and we'll make this phi 1. Okay, there you go. All right, let's go back to where you guys can see what I'm doing here, and we'll go back to. I got to make sure that I actually let you see what I'm. There's me. Too big. All right, share screen. Entire window, Chrome tab. Alrighty. There we are. Okay, so. Yeah. So what do we got here? We've got the golden ratio. So let's do this here. So this down here, okay, we're going to write this. We're just going to focus on this bit here, this 1 over x squared. Okay, we're going to write that in terms of its factors. So let's do this. So we've got 1 over, okay, and then we'll do, so we got the zeros were phi, and we're going to call it phi bar, the other one. Okay, 1 minus phi, 1 minus phi bar. Okay, and so those are our, there it is, factored. Okay, and what we want to do in order to make this convertible into another infinite sequence and another power series is we want to convert this to partial fractions. Okay, so we're going to do that. Make sure that you can see what I'm doing here. So hang on here. I'm going to cheat. I'm going to check my notes. I wrote this up months and months ago. I just want to be sure now that I'm doing this live that I don't really mess up here. So I'm going to check my cheats. I can just share you what I wrote. I can also link to the article later on here. Hang on here. Okay. No, it's not. Hang on here. That's not it. Go into my stories. There we go. Published. I'm just going through my blog here where I wrote this up some time ago, and I want to be sure that I get it. I don't mess up here. So sorry about that. Talk amongst yourselves while I do this. No, I think I did it. Think like Archimedes. Speed of light. There we are. Okay. Oh yeah. Okay. I actually published an article on this September of 2020, but actually, the way my method in that article was actually nastier than this one. So let's. Okay. Alrighty. So. There we go. X. Oh, right. Because everything is negative. Okay. Did I lose you? Did I lose you all? Oh, good, you're still here. Okay. So, right. Because normally we would write, we'd write our factors as x minus the thing, but our value over here was negative. So we have to do x minus the thing. So it's x plus phi and x plus phi bar. Okay. And I will send a link. I will put a link in the description at some point to the article I wrote in which I'm referring to this, because so far everything here is the same. Okay. But now we want to convert that into, the sum of partial fractions. I don't know if you've seen partial fractions before. Say yay or nay or boo if you have. I don't know. Okay. All right. So going to convert that to partial fractions. Okay. So how do we do that? Well, we need a common denominator. What's the common denominator going to be? Well, it's going to be this thing down here on the bottom. Okay. So let's do a times x plus phi bar, okay, plus b times x plus phi or phi or however you say it, all over the common denominator, which is the thing that we started out with, x plus phi bar. And now let's work this all out, and we end up with AX plus A times phi bar plus BX plus B times phi all over the stuff. All right. And now we already factored out the A. That didn't help us. So now we're going to factor out the X's. Okay. So we're going to go all over the stuff. We've got A plus B all times X. Okay. And then we got plus, factored out the X. We got, hang on here. Okay, so that factors out the X. Okay, and then we've got plus A phi bar plus B phi. Okay, all that. Is that right? AX, BX. Okay. Check my notes. I'm going to cheat. Okay. Okay, gotcha. See, I'm making this more complicated than it needs to be. Okay, so remember all this stuff on top. Here's the thing. All this stuff on top, okay, equals 1 over business. Okay, so let's go over here. Okay, so we've got A plus B all times X plus A phi bar plus B phi equals 1. Okay, we're good with that? Now, the thing is, we treat this like it's a polynomial. Okay, so that equals 0 times X plus 1, because the first question we ask is, well, what is our X term? Okay, and we go, oh, A plus B must be 0. So A plus B must be 0, which leads us to A equals negative B. Okay, and now I gotta see what I did next here on this. Okay. Gotcha. Okay, now we're gonna go back up here. Back to, this is why I do all this stuff. You usually do all this stuff ahead of time, because now I get to deal with the all over the map thing here. Okay, now let's just say that this equals 1, okay, for any value of X. Okay, so that should be a phi bar. Okay, so what we do here is we go, okay, well, let's choose a value for X. So let's choose X equals phi bar. Okay, so because this is good. This is stuck. Okay, so because X equals this top bit equals 1 for any value of X. So let's choose X equals phi bar. Okay, and so that's, in fact, let's do better. Let's make it negative phi bar. So this means that A times negative phi bar plus phi bar equals, plus B times all this stuff. X is negative phi bar, so negative phi bar plus phi equals, I'm live streaming. Okay, so that ends up being 0, okay, plus B times the sum of these two things, okay, equals 1. And this, I'm totally getting lost here. I've got the thing that I wrote. Maybe I should just show you that. Oh my goodness. X equals negative phi bar. B times negative phi bar equals 1. So, now. So A equals 1. Oh my goodness, yeah. Okay. It's just so complicated. Okay. Are you following this? My goodness. Okay, so B times, and I'll put the phi here, minus Q phi bar equals 1. Okay, so B equals 1 over phi minus, I told you that this was long and convoluted, B minus B over phi minus phi bar, okay? Which means that, remember, A is negative B, so A equals negative B, so that equals negative 1 over phi minus phi bar. Let me just check, make sure I didn't lose my, it's good enough. Okay. My goodness. Okay, hopefully you can still see this. If not, I quit. Okay. You're still hanging in on this. Excellent. You are a diehard. Okay. Because I really want to stop. But okay, so what did we have here? We've got our original A over X plus phi plus B over X plus phi bar equals 1 over this horrid thing. Right, over X plus phi plus negative 1 over X plus, I think I'm getting my phis and my phi bars mixed up. Okay, this did work, and I'm just checking my notes. It's just this trying to think and live stream at the same time. I'm going, oh my goodness. Okay, so there we go. So we got B and we got A. Okay. Oh, those should be minuses. Minus 5 phi bar. Okay. Oh, hang on here. A equals B equals. Oh my goodness. You know, I should just cut and paste it from the article here and put it up here so you can all see it. Okay, I'm getting lost. I totally am getting lost. I'm sorry. I'm going to share the article. You can just watch this. Okay, I'm going to show this to you because I am totally getting messed up here. So this is not how to do a live stream. People who are watching live stream, this is not how to do it. Okay, so okay, I'm gonna share the article because I'm just going back and forth and I'm totally getting lost. Maybe this isn't for me. Share screen. Okay, Chrome tab. There it is. Okay. The thing is, I did this a little bit differently. Okay, are you watching this? Can you see the article? Okay, and I'm actually I'll put it up entirely. Okay. This is something I wrote. Okay, so I mean, I solved those. This is where I started to get messed up, and I used I used h of x here. Okay, and so I'm solving for a and b, and the whole point is I end up with these partial fractions. Okay, for a and b, but then I simplify a, and a becomes minus 1 over square root of 5. This was just too much to plan to do in a live stream. And b becomes 1 over square root of 5. So then we end up with, there's our negative x, because remember we had factored out negative x, and this whole mess, which, you know what, I'm going to cut and paste it into our thing here. Hang on here. Okay, take out the h of x. And I'll do that because I need to skip ahead, because I need to finish this like before tomorrow. Okay, so I'm going to put that into the whiteboard. And then, you know, what I'm going to show you next is, let me share. Nope. Okay, let me bring that up again. And I'm going to share the whiteboard. Share. Chrome tab. Okay. Okay, so let's make sure you're looking at the same thing as I am. Yeah, okay. So this is what we're supposed to end up with, okay? And up to this point, pretty much in the article, which I'll link, I'm following the same thing. And then in the article, I take an unnecessarily difficult approach to resolving this. And it works, but it starts involving, it involves the, binomial expansions and negative numbers in the exponents of the binomial coefficient, and it works and it's cool, but it's just nuts, and there's no reason for me to do it that way. So instead, I'm going to take each of these chunks, okay, and I'm just going to convert it easily. Somebody on Math Stack Exchange said, "Why didn't you do it this way?" I went and I look at it and go, "Yeah, that'd be a good reason." So I'm going to take each of these bits and I'm going to convert this into, okay, an infinite sum. And what I'm going to go by that is your standard power series is 1 minus r. Okay, that's your common ratio. Okay, 1 minus whatever the common ratio is. Okay, so if your common ratio is whatever here, so hang on here. So what does that equal to? So if I've got this as being x, we'll make that x. Okay. Okay, so hang on here. Check some notes. Just check something. Okay. I'm moving away from the complicated way that I did it here, so I just want to make sure that I'm doing it right, because I don't have notes. Okay. Okay. Yes. Okay. Okay. My goodness. Okay. And you know what? I think I'm losing my concentration. So I think I'm going to call this a day, and I will not post this. Okay. You've got to deal with this as a common rate, with R being the common ratio, except you know what? It's, okay, in this case, it's X is the common ratio. Okay. So I'm losing my concentration. I should have brought better notes before trying to do this. And I knew that this was a long, convoluted thing that I've tried to do before. So Wolf, are you still there? Thanks for sticking for this. I will post a link in the description to the article that this is supposed to be doing. And I'm going to call it a day because I'm totally losing concentration. I've been at this for an hour and I'm just muttering, and I'm not going to post this as a thing. So thank you for showing up, and now you're going to. So anyway, this did not work out. And I'm going to end the broadcast. Okay. Oh, actually, you know what? Let me post a link right away here. Okay. So that you get it. Thanks. You know what? I appreciate your supporting me and showing up for this. Okay. But I think in the future, I need to be a lot clearer rather than do it off the top of my head. Thinking on the spot. So you know what? This is the friend link to my article on Medium. If you want to go and check it out, the only issue with this is right at this point here, I use a much more complicated way of getting it. Okay, so I'm gonna post you the Math Stack Exchange article if you're interested in this. Then you got that too, Math Stack Exchange. This is because I actually went there and when I was writing this article and to check some of my thinking, and let's see here. So I'm going to post that, and so you can see that as well. Some of the solution there that this person said. Let's see. Fibonacci general term. How do I bend this broken definition? So I was having trouble with it. So here's the discussion, okay, on the Math Stack Exchange. And so I'm going to give you that too. Okay. And there it is. And in particular, take a look at what this fellow said. And I'll just put it up on the screen right now. Here we go. Actually, no, I should just cite this. Let's see here. Somebody had a really good, actually, no, you know what? Just go down because there's a few answers, but look at the one that I checked off as the correct one, because he did what I was trying to do here. And he used the formula for the geometric series. So I'm going to share it, and I'll put that down there to save you a lot of grief. And so that's going there too. So my apologies for not making this really easy to follow in my video. So, but check out my daughter's telling me I'm talking too much. So check out the links I've just posted. So the first one is my write-up on this whole thing. And then the second one, if you follow that, right after I do the partial functions, the partial fractions, what I do is interesting. And it's just interesting in its own part because I'm using these binomial coefficients with negative numbers. But the simpler route to this is in the math stack exchange, in the discussion there. So thank you. Thank you. I'm going to go now, and maybe I'll leave this here and somebody can follow it along and hear me ramble if they want. Okay, I'm going now. Bye-bye. I got to end broadcast.